recording this session. Yeah, okay, so okay, you should be able to see my screen now. Okay, so this is if I go back to this is from the lecture notes. So I'm actually going back to chapter 3. Okay, so in the order I actually skipped over chapter 3 to concentrate on stability, just because to help you a bit with the coursework assignment. So I'm just going to go back to chapter 3. And I'm actually going to go to the tutorial exercises. Okay, and I thought I'd talk about the tutorial, the solution to question 1. Okay, and this will help you understand some of the difficulties involved with actually using implicit Runge-Kutta methods. So this is on page 37 of my part of the notes. Okay, so we have an initial value problem. It's very simple. I deliberately made them simple because we're still kind of getting the grips of this method. So derivative of y equals 4 times t times y. The domain of t is 0 to 1, and our initial value of y is 1. Okay, so I'm just going to write down what we have. So we've got y dash is equal to 4ty. We've got an initial value of 1, and we're asked to use a step length of 0.1. Okay, so what we're going to do is use an implicit Runge-Kutta method. And if I just go back to the, that's not the right one. If I go back to the question, we're asked to use a Radal type 1a. So what I'm going to do is I'm going to just write the butcher tableau on this screen, just so we're reminded of what the butcher tableau is. So that's 0, 2/3, and my c values, 1/4, minus 1/4, 1/4, and 5/12 are my a values, and 1/4, 3/4. Okay. Well, when we're using implicit Runge-Kutta methods, okay, instead of using k for our stage values, we use what we call big YI. Okay, and this is just to help us simplify things. So big YI is equal. This is for a general Runge-Kutta method. Yn plus h times the sum of s. Oh, not s. J equals 1 to s aij, and then we have our function f of tj, sorry, plus sorry, not tj at all, or ti is tn plus cjh, and our second argument is going to be yj. Okay, so this is similar to what we did when we looked at stability. Okay, usually with a Runge-Kutta method, our stage values are k1, k2, etc. But for implicit methods, it's useful to if we rewrite them in this form. Okay, if you're not sure where this comes from, just check out either the video lecture or the notes. Okay, so for this method applied to this ODE. Okay, so what I'm going to do is I'm going to write down what y1 and y2, or big Y1 and big Y2 are. So we have y1 is going to be equal to our current value of y, which is yn, plus our step length. And what I'm going to do is we've only got 2 stages, so remember s is equal to 2. I'm just going to expand this out. So I've got a11, well, our a11 is 1/4. So we have 1/4, and that's going to be multiplied by our function. Now our function is 4ty, so I'm going to have 4, but instead of t, we're going to have tn plus c1h. Now c1 is 0 in this case, so that's going to be plus 0h. I've left it like that just to, ordinarily we just write tn, but I've left it with 0 just to show you where that comes from. And then that's multiplied by y1. Okay, so you notice our ODE function was 4 times t times y, so that's your 4, that's your t, and there's your y. Okay, that's for the first one, and 1 we have minus 1/4, so I just put a half. So if I change that to a minus, we have minus 1/4 multiplied by 4, And this time it's going to be Tn plus C2H. So that's going to be Tn plus 2/3 H. And that's going to be multiplied by Y2. Okay, so that's our first stage value calculation, and our second one is similar. So again, we're going to have Yn. This time, instead of I is equal to 1, we have I is equal to 2. A21 is 1/4. All this function is exactly the same. Y1. And this time I'm going to have plus, but A22 is 5/12. So that A22 term there is going to be 5/12. And this function is going to be the same. Okay, so we have these are two implicit relationships. So we've got a Y1 there on the left, and we've got a Y1 on the right. We've got a Y2 on the left there, and we've got a Y2 on the right. Now, fortunately, in this case, this is a linear system. Okay, so what we can do is we can rewrite it so all of our known values are on the right-hand side and our unknown values are on the left. So what I'm going to do is I'm just going to simplify these to start with. Okay, so if I simplify the right-hand side for equation 1, we're going to have, well, 1/4 times 4 is obviously 1. So we're just going to have Tn times Y1. Okay, and our second term in the bracket here, but again, 1/4 times 4 is 1. So we're going to have Tn plus 2/3. Oh, forgotten an H. Actually, I'll just redo that. That should be 2/3 times H, and that's times by Y2. Okay, this is similar for our second equation. That looks like a half there, doesn't it? That's meant to be Y2. So Yn plus H. Again, we just got Tn Y1. Okay, so that's all of that simplifies to Tn Y1. This time we've got 5 plus 5/12 times 4, so that's going to be 20/12. Common factor of 4, so that's going to be 5/3 times Tn plus H times Y2. Okay, so that was what equation 2 gave us. Now what we can do is we can, I want all terms which involve Y1 and Y2 on the left-hand side of the equation. So call that equation 3 and 4. So for equation 3, okay, we're going to have Y1 minus H times Tn. So we're going to have 1 minus H times Tn times Y1. Okay, so again, my y's are looking like fractions. I'm just going to tidy that up. So that's my 1y1. So that's that one, and we're going to take minus htn over to the left-hand side. So that's going to be minus htn y1, and then added to that, we're going to have plus, because that's a negative there, h, that's that one, times tn plus 2/3 h times y2. Okay, and that's going to be equal to yn. So all of that term, all of those terms there have been taken over to the other side, and I'm just left with yn, which is my known. That's the only term I know what the value is. Okay, do similar for question 4. So start with y1. We're going to subtract h tn times y1, so that goes over to the left, plus we've got 1y2 there, and we're going to subtract 5/3 times h, so that's going to be tn plus h, and that's going to be all that's multiplied by y2 equals yn. Okay, so what we have now is we have a linear system, and we can rewrite this as a matrix equation. So here, if I'm going to write it as a matrix equation with y1 and y2 as the unknowns. On the right hand side I've got yn and yn, and in our matrix I've got 1 minus h tn, and I've got h tn plus 2/3 h there. Lower left I've got h tn, and lower right I've got 1 minus 5/3 h tn plus h. Okay, so we have a linear system. So solving this linear system will give us our values for y1 and y2. Okay, so at this point is when I'm going to reach for MATLAB, because there's far too much for me to calculate for my liking. Okay, so I'm going to bring in MATLAB, the live script, just to do the calculations for us. Okay, is that large enough for you to be able to see? Would you like me to blow it up, or is that okay?
Can you make it a bit bigger, please?
Yeah, no worries. How's that? That's still okay. So can you see what I've written there?
Yeah, that's a bit better.
A bit better. Okay, more than merry. I'll blow it up. Okay, so I'm going to start with entering in some of our. Actually, I'm going to use yn. Actually, I'll call it y0. So our initial values was of h, y0 and 1. Now what I'm going to do is I'm going to solve this system down here. Okay, so I'm going to enter in our coefficient matrix. Actually, I'm going to change these to t because I might want to use them again. So I'm going to assume that y and t is yn and tn. So that's 1 minus h times t. Now I've got h times t plus 2/3 times h. And yeah, and on the next line I've got minus h times t, and I've got 1 minus 5/3 times h times t plus h. Okay, so just that gives us some values. Should really check whether that's correct, but hopefully it is. Our right hand side vector b is going to be whatever our value of y is. Okay, so you can see our right hand side vector is just yn and yn, so whatever our value of y is. So you can see that's just a 2×1 vector of 1s. Okay, now you could there are a number of different ways to solve a linear system. I'm going to cheat, or somewhat cheat, and use MATLAB's solver, and that's the backslash. So you might have seen this before. A/b just tells MATLAB, let's solve the system. And if I do that, you can see that we have our values. This is y1, and that's y2. Okay, so that's our solution for our stage values. Okay, so for an implicit method, it involves solving a system of equations. Okay, so I'm going to go back to the to my scribblings. Okay, I'm just going to sort of open a new layer, and what we have is, okay, so we've solved that system. So we've got 0.9932, and y2 was equal to 1.0169. Now our Runge-Kutta method. Okay, alarm going off around here. Our Runge-Kutta method is I equals 1 to s of bi multiplied by f of tm plus c on h yi. Okay, so that's using the big Y. We rewrite the Runge-Kutta in this form. So for our first solution, we've got our initial solution y0 plus h, and I'll just remind myself what the butcher tableau was. Okay, so that's that one there. So it's b1. Oh no, it goes as soon as I start writing. Okay, so b1 was a quarter. So that's a quarter, and if you remember, what we were solving for is 4ty. Y dash equals 4ty. So that's a quarter times 4 times t0 plus 0h. That was times by y1. And b2 is 3/4. And that's 4 times t0 plus 2/3 h times y2. Okay, so just to remind, where did I get those values from? Okay, so C1 is 0, C2 is 2/3, and B1 is 1/4, and B2 is 3/4. Okay, so again, I'm going to bring in MATLAB to help us with the calculations here. Okay, so bringing in MATLAB. So what we were doing there is we were solving. We were solving the stage values, and what I'm going to do now is update the solution. So solution, our next solution is what we have here. So that's equal to our current solution plus h multiplied by 1, which was 1/4, times 4, and that's multiplied by tn, or t, times y1. Okay, y1, so it's the first element of our y solution there. Okay, and that's plus 3/4 times 4 times t. I'm going to have to sort of make this a bit wider. That's going to be t times 2/3 times h, and that's going to be multiplied by y2. Okay, so if I run that, y1 is 1. That's not good. So for some reason I've got, so just double check what my y is. It shouldn't be 1. Okay, so I've got that. So just double checking. Should really put 0h. So 1/4 times that. Just double check all of my brackets are correct. 3/4 times 4. There we are. I had t times rather than t plus. There we go. Okay, so that's solving for one step of the method. So if I just bring in the question again. Okay, you can see here that's solving for one step. So you can see we had to solve that linear system to calculate the stage values, and then we update the solution. Now part B says write a MATLAB program to compute the solution over the whole domain, so 0 to 1. So what I'm going to do is actually adapt what we've got here to solve for the whole domain. Okay, so I'm going to adapt this. I'm just going to reduce the font size a little bit just so we can fit a bit more in. Okay, so that's clear. This A matrix, that is going to change because that's going to rely on t. Okay, so what I'm going to have is I'm going to have a while loop. So I'm going to say while t n is less than t span 2. So I've got to define what t span 2 is, or t span. So that's going to be our domain. Oops. And our initial value was 1. So I'm going to say I'm going to change y to be a vector. So I'm going to have to make some changes to our code. So the first element of the y vector is y0, and the first element of our t vector is our first element of t span. And I'm going to set n is equal to 1. Okay, so I've got a while loop here. I'm just going to tidy this up a bit. So first we need to solve for the stage values. So I'm just going to make that a bit more correct. Okay, so our A matrix changes in each step, because Tn is dependent upon Tn. So wherever I've got T, I need to change that to the nth value of T. Okay, so that is our coefficient matrix. Likewise with our B vector, so this is our right hand side vector. So if we just go back to this layer, you can see that was that right hand vector there. Yeah, so solving for the stage values. Okay, so that will give me our solution for y. Now we update the solution, so that's going to be yn plus 1. Okay, that's going to be yn plus h. So wherever I've got tn, or t, I'm changing it to tn. And what I'm going to do is just put a line break in there so we can see it a bit better. Okay, and we also need to update our, oh, where's my thing gone? Oops. Oh, my cursor's not, oh no, MATLAB doesn't, seems to, oh dear. I think MATLAB might have frozen on me or something, is it? Oh no, I'm just, yeah, that froze for a second. So we also update tn, tn plus 1 is equals tn plus h. So this is very similar to the explicit ones. The difference is when we solve for the stage values, we have to solve that linear system. Okay, so if I run that, just to check there's no errors, and I'm noticing MATLAB's not running particularly fast for me at the moment. Don't know what's happening. That might be, I'm just going to see if I can pause that and stop it. Yeah, oh dear, I think my MATLAB seems to be running a bit slow for some reason. Oh, it's giving me a green line. I've never seen that before. I'm just going to stop that there. Okay, so just double checking. What I'm going to do is just make sure that we're actually out. It's actually running through something. Okay, it is running through something. Okay, so it is actually doing something. Ah, I see. Anybody spot the infinite loop? Okay, so okay, I started MATLAB running an infinite loop then because I didn't update our n value. Oops. Never seen that green line before. I don't know what that is. Okay, so I'm going to stop that there. Okay, so what was happening is I wasn't updating n, so therefore I was never updating any of these. So if I run that once more, yeah, it's finished. Okay, so what I can do is just quickly output our values for t and y. Okay, we can see we have those, and I can do a quick plot. Okay, so that's my solution. Okay, it's actually gone over. Oh, that's interesting. It's actually gone over the solution, probably due to a computational rounding. So what to stop that? Okay, so I'm going to ensure that t does not exceed t span 2, and the way we do that is we set h to be the minimum of h, or t span 2 minus tn. So if I run that again, and yeah, you can see it stops at 1. Okay, so that's my solution using that implicit Runge-Kutta method. Okay, I better tidy up my code. Oop. Okay, so that's using the explicit Runge-Kutta method. It's always good to check our code to see if it actually does work, and one way to do that is check it against, let's say, ODE 45. So I'm going to solve using ODE45. So to do that, what I need to do is actually define what the ODE function was. So I need to define this function here. So y dash equals 4ty. So okay, so that's defining my ODE function. I'm not. No, I'll try that later. So what I'm going to do is I'm going to call the ODE45 solution T1 and Y1. So it just has to be different from T and Y. So I'm using the ODE45. ODE function was F. T-span is T-span. And Y0 is the same. And I can plot T1 against Y1 as well. Okay, good news is you can see that if I put a legend onto the plot. So the first one was the Radal 1A method, and the second one was ODE45. Okay, so you can see here, but the Radal, which is the blue line, closely agrees with ODE45, which was the orange line. Okay, there is a bit of separation here. ODE45 is used adaptive step size control, so it's used a smaller step length. Now we could sort of replicate that, and let's sort of use 10 times the number of steps. You can see they're virtually indistinguishable. Okay, so as you see there, it's very little difference between Radal 1A and ODE45 for using that using the smaller step length. Okay, obviously implicit Runge-Kutta methods are more expensive to calculate because this calculation here, okay, that's quite an expensive calculation as opposed to explicit methods, which is just a straightforward function evaluation. Okay. Right. Are there any questions regarding that sort of solution method? Okay, so that was actually a very easy, believe it or not, that was a very easy ODE to solve. Okay, it was easy ODE to solve because when we look at our stage value calculation, we had a linear system. Now that's not always going to be the case. Okay, also when we look at systems of ODEs, because this one we've just done was a single ODE. Now, when we look at systems of ODEs, it gets a little bit more complicated. So I'm just going to talk through what we do for systems of ODEs. This is similar to what I put up on the lecture recordings. Okay, so that now when we look at systems of ODEs, to calculate the stage values, we use Newton's method. Now, Newton's method you may have seen in your second year. It's a method for finding the root of a function. So if g is our function, what we do is we have a guess for the root, which is xk. If we calculate g at xk, find its tangent, and where the tangent intersects with the x-axis, that's our new estimate, and do it again, and eventually we'll get to the actual root. Okay, well, we need to use that for a system of equations. Okay, so if we have multiple functions of g, of multiple variables, x1, x2, etc. Okay, the equivalent form of Newton's method is this. Okay, so this J matrix, this is a Jacobian. Okay, you're well used to Jacobians by now. Okay, but the problem is we've got an inverse calculation here. That's going to be expensive. Let's say you have 100 ODEs to solve. You'll have an inverse of 100 by 100 matrix, just far too computationally expensive. So we use a little trick. We define a change in our estimates, delta x, and we rewrite equation 3.8 in this form, which is a linear system. Okay, and then we use whatever linear system solvers we have available. Usually it's LU factorization. And to solve for delta x, once you've got delta x, you just add it to the current guess value. So remember, x is a vector, and that's an n by 1 vector, where big N is the number of equations in your ODEs or in your system. So we're going to use that with implicit Runge-Kutta methods. Okay, so one thing I've also got to introduce you to is the idea of the Cronetta tensor product, or often known as just tensor product. And this is a way of writing matrices within matrices. So it's a shorthand. So the tensor product is denoted by this, what we call an O times. It's just a time symbol within a circle. For example, for these two matrices, for every element in the first matrix, I'm doing a scalar multiple of the second matrix. Okay, so there we have A11 times the second matrix, A12 times the second matrix, etc. And so this will give us a 4 by 4 matrix. So this is the output of this tensor product. Okay. So what we want to do is we want to be able to apply our implicit Runge-Kutta methods for solving a system of ODEs. Okay, so this system here. Okay, so this is going to be a vector of y, y1, y2, etc. So these are all your equations. And we're also going to have some functions. So f1, f2, etc. are all functions for our system. Now, ordinarily, these would be our stage values, and this would be how we update y. Again, similar to the last example, we simplify these. So we let yi, big yi, be our stage values. Okay, and then we can rewrite our Runge-Kutta method in this form. Okay, right, so we just seen in that previous example, but for a single ODE, we had to solve a linear system, or we had to solve a system of equations for our big Y values. Okay, let's see what we have to do for a system of ODEs. Okay, so for each of our stage values, let's say y1, for example, we have yn, which itself, that is a vector. So you see it's in bold, that yn is a vector, and that's going to be equal to this summation, and this f is also a vector. So we've got vectors within vectors. So for example, this first summation here, that is this vector. Okay, so remember our bold F is the vectors F1, F2 up to Fn, and we got that summation as well. So it starts to get the combinations start to get quite complex. So this is where tensor products come in. Okay, so we can rewrite the summations. So this summation, these summations here, we can rewrite as this matrix multiplication. Okay, so for our first row, okay, this is for y1, we have this as our as that summation. So for all other rows, or for all y2 up to ys, we have this form. Okay, so this is a times in. So all of these INs are n by n identity matrices within this whole matrix here. Okay, so that's where that tensor product comes in. So that's the tensor product of A and IN, the n by n identity matrix. Okay, so we can now write our implicit Runge-Kutta methods using tensor products and using vectors. So we're going to define y, our vectors of stage values. Remember, for each of these, y1 is also going to be a vector of n, big N, where big N is the number of systems in our number of equations in our ODE system. Big F is related to our functions, and each one of these is itself another vector. And E is just a vector of ones. Okay, so that just simplifies the notation somewhat. Okay, so we can rewrite this equation here as this. Okay, so our vector of ones multiplied by yn, so that gives us this vector here. We've already seen where this comes from, and this vector we've got written there. Okay, so that's our stage value calculation, and this is how we update our solution. Okay, so this B transpose tensor product with in, okay, that's just replacing the summation within the updating of the Runge-Kutta method. So we apply Newton's method to solve for our stage values. Once we've got the stage values, we then plug them into this formula, and then that updates the solution. Unfortunately, there's another complication. Okay, let's have a look at trying to apply Newton's method to this. Okay, so we want, if we go back to the previous where I spoke about the Newton's method, we want some function or some vector g of x, and that's what we're going to solve for. So we want to find the root of that function g. So if I subtract y, big Y, from both sides, we get our function g, and we're finding the roots of this. Now we need to differentiate this or calculate the Jacobian matrix for this in order to use Newton's method. If I just go back and show you why, back up to Newton's method, the matrix form of Newton's method. So we need that Jacobian matrix. So that's the Jacobian matrix. So that's just this differentiated with respect to big Y. Okay. Now, big F differentiated with respect to big Y is equivalent to this. Okay. So sorry, this 3.16 is equivalent to this. Each one of these is itself a Jacobian matrix. Okay, so you can see it starts to get really quite complicated in terms of there's matrices within other matrices. Now, another problem we have is that we'd have to calculate at each step in our Newton's method, we'd have to recalculate all of these Jacobian matrices, and these are all different. So that's too computationally expensive. Okay, so we need to simplify this. So we use this approximation. So this is the Jacobian of our initial system of ODEs, and that's the tensor product between that and the identity matrix. Now, this isn't strictly speaking correct, but it's good enough for our Newton's method. You've got to remember our Newton's method is itself a approximation method. Okay, so 3.16, which is our Jacobian, that's simplified to this by using this simplification. Okay, so that's relatively straightforward. That's an identity matrix. We know what our step length is. That's our A matrix. That's another identity. That's another identity. So this is our matrix from our original system. Sometimes it's not possible, or sometimes it's just too tricky to calculate that if we want to get a solution. So what we do tend to do is use a finite difference approximation for each derivative in that Jacobian. Okay, so quite often, for some sophisticated implicit Runge-Kutta method solvers, they may give the option to say, do you know what the Jacobian is, or do you want me to approximate it? So all the MATLAB ones, for example, you can actually ask it to use a specific Jacobian. Okay, so that's just a first order finite difference approximation. Okay, so once we calculated the Jacobian, okay, we know what g of y is because that was this function here. This is a linear system, so we solve that linear system for delta y, so that's usually using LU decomposition. And then we calculate, we update our estimates of our stage values by just adding delta y onto k. And we continue until the norm, because remember delta y is a vector, we continue until the norm of the vector is less than some tolerance. So that's quite a lot to take in. It is quite an involved thing to actually calculate and to code up an IRK method. So here's the steps. Okay, I'll just run through these. So kind of similar setup to any other ODE solver. For when we go for the when we go through the steps of the Newton's method, we initialize our stage values to be our vector of ones tensor product with our yn vector. We then calculate our Jacobian matrix using, remember, that's our Jacobian for our individual for our system of ODEs. That may need approximating, it depends what your ODEs are. Initialize an error to be 1 because we're going to go through a iterative cycle. We iterate until whilst the error is greater than tolerance. So we calculate GY, we solve our linear system, we update Y, and we calculate the error, which is a norm of delta Y. So once you've got that, okay, we can then update our solution vector, update our T vector, and update our counter. Okay, so I'm just going to talk through the solution, the example here. So this is, as always, start with a simple example just to understand the method first. So here we've got a quite a simple two system of 2 equations. We've got our 2 initial values here, and we're going to use the radar 1A method, which we used at the beginning of this webinar for the single ODE. Now, in this case, looking at our system, it's possible to differentiate this. Okay, so if we calculate Jacobian for these 2, you can see it's 2, 1, y2 and y1. Okay, so that's fairly easy to do. Calculate Jacobian matrix. So I4, now this is n times s number of elements for our identity. So we have 2 equations and we have a 2 stage method. So that's 2 by 2, so that's 4. So that's where that comes from. A tensor product with I2. So for each element in A, which is a quarter minus quarter, a quarter of 5/12, is multiplied by the 2 by 2 identity to give us this 4 by 4. And for this one, so this is our Jacobian. That's tensor product with the 2 by 2 identity. So that gives us this matrix. Now for the first step, we know what our initial solution is for y1, y2, and we know what h is. So we plug that into our Jacobian and we get this 4 by 4 matrix. So now we proceed to Newton's iterations. So just to, we need a starting value for big Y, so we tensor product with y0, and that gives us this if we calculate the function. Okay, then calculate G for our first guess value for Y. Okay, so that's all of this. So plug that, plug it into MATLAB. It's too much brute force calculation to do it by hand. And if we solve for that, it gives us delta Y are these values. Okay, so we update our big Y and we do the same thing again. If you do the same thing again, the delta Y is 10 to the minus 13. Okay, so after just 2 iterations, we converge to a solution for big Y. And we plug big Y into our updating our Runge-Kutta method, and that gives us that solution. Okay, so I mentioned, you know, it's a lot of calculations, especially using Newton's method. So I'm just going to talk through the MATLAB code for that. Okay, so these are the MATLAB codes I used to calculate all of these. I didn't do these by hand at all. So define the ODE function. So f is your standard way of defining the function. Okay, big F, now that's this one here. Okay, the reason why we need big F is it's slightly different because we're using the stage values Y and big Y. Okay, so big F, notice it uses big Y. Okay, and that in turn uses our ODE function. So big F is a vector of F's, which is in turn a vector. Now we got the Jacobian, which I've called JAC or Jack. and that Jacobian was 2, 1, y2 and y1. That got that from, where are we? Here. Okay. Same thing again. Define IVB parameters. Excuse me, my cat's just got in the way. Okay. Define the Radal method. Okay. Initialize solution arrays. This is all should be fairly standard for you. Okay. One thing you'll notice here is cron. Now this is MATLAB's tensor product operator or function. So remember, it's Cronetta tensor product. Again, cat's getting in the way. So this is a Cronetta tensor product. So that was the product between E, which are vector of 1s, and our initial or our current solution yn. This is that Jacobian. So that's J of big Y. So I'm just going to scroll all the way to here. Not here. Oh, crikey. Yeah, that's this one here. Okay, so that's there. So notice I'm making use of MATLAB, the Cronetta product. Oh, get out of the way, Cavendish. My cat's being very persistent. Yeah, so that's calculating J, loop through. This is the Newton's method. That's it. I've forgotten the name of the method there. Again, lots of Cronetta products. Okay, using the big F. So remember, this is a function of functions. I've cheated. For delta Y, I've used the MATLAB solver. I should really have used an LU factorization routine there, but I've cheated a bit. Update your or update the guess for the estimates of Y and calculate the error, which is just a norm of delta Y. Okay, and then you just update the solution. Okay, so that's how we use implicit Runge-Kutta methods for a system of equations. So you can see the actual length of the program is not that much, but it takes a lot of sort of understanding, and it took me a while actually to read into this to actually fully understand what's going on with an implicit Runge-Kutta method. Okay, what we can do is if I go back to this, where was it? The initial. Let's have a look at MATLAB's solver routine for this. Okay, so I'm just gonna, just out of interest, I'm not sure what it is, but so what I'm going to do, I know you can't see that, is I'm going to define that function. So that's going to be ty, and that's going to be 2 times y1 plus y2, and our second is going to be y1 times y2. So that was the function t-span. Let's say it's 0 to 1. I haven't actually got a t-span there because I was only doing the first term, and we're using h as 0.1. Actually, I'm going to let MATLAB decide what h it wants to use. Y0 was 1, 0. Okay, so what I'm going to do is use ODE23, which is an implicit method, to solve that. ODE fun is F, T-span, Y0. And what I want to do is actually get it to output the stats. So ODE set is an option, and stats on means it's going to output the stats. Okay, so I'm going to run that. ODE23 wasn't it? I can't quite remember what the ODE113. Trying to find one which is an implicit method. Here we go. Right. So actually, I can plot the solution now, can't we? Okay, so that's if you're interested, that's a solution to that problem. Seems that y2 is just all on the zeros, but we're not too worried by that. What I wanted to show you was the fact that here we've got all these solver stats, but when we're using an implicit method, Okay, you can see, but we've got 11 partial derivatives. Now these partial derivatives are the calculation of the Jacobians, and we've also got LU decompositions. So those are the solution of the linear systems in to calculate Newton's method. Okay, so 11 LU decompositions because our Jacobian changed. So remember from LU factorization last year, when your coefficient matrix changes, your L and your U matrices change, and it required 33 solutions of linear systems. So there were 11 steps. So each step probably required 3 iterations of Newton's method to calculate the stage values. So if you ever see additional sort of in your solver stats, you know, with partial derivatives, compositions, etc., that shows that this is an implicit method. It shows that it's having to do Newton's method for that. Okay, right. There was a lot to take in there. I think, in my personal opinion, I think implicit Runge-Kutta method is probably the hardest part of Runge-Kutta methods. They're very elegant in general, but there's a lot of niggly sort of detail to take in. So what I suggest you do is you kind of read this chapter quite carefully. I'm not expecting you to sort of derive any of this. And in the if I bring up the assessment, for you. I know that's quite small text, but I'm just going to bring up the assessment. All right. So it says here on B part 2, write a program in MATLAB or Python if you want to solve this using the IRK method given above. And it's constant step length of h equals 1. Okay, so you can adapt the code which is given in the notes to be able to do that. Okay. Right. Any questions about what I went through today? Now, like I say, I wouldn't be surprised if you're feeling a little bit confused at the moment. It does take a while for that to embed. Take the silence as a no. Okay. How are you getting on with the assignment? Is there anything you quickly want me to sort of clarify about the assignment for my question? Again, I'll take silence as a no. No. Okay, so I think we'll leave it there then. Yeah, we'll keep an eye on your emails and your individual timetable through my MMU. We don't quite know what's happening with the seminar, so keep an eye on that. There may be a change. But okay, take care everyone, and I'll see you next time whenever that'll be. Yeah, is it tomorrow? Or yeah. Okay, see you. And just stopping the recording.